right? So last time we started talking about four vectors. Those of you on Zoom cannot see this loop, this line integral up here. Where the idea is that, instead of dealing with, just the time variable, the x variable, the y variable, the z variable, you squish them together. And in order to conserve Lorentz invariance when you do a dot product of these four vectors, what you do is you define a contravariant four vector where it's just, the first element is t, which is index 0. Okay, the second element is y, and then second element is x, y, x, and then y, and then z. Hopefully that makes sense. I think on the screen it's a lot more clear than what I'm saying, right? But this is, your typical, three vectors, right? So that may be your R with a little arrow on top like that. But you just tag on the time component to it. But the interesting thing is that when you do a dot product with this by itself, you don't get a Lorentz invariant. So therefore, what we want to do is define something called a covariant. So the stuff down here is the covariant four vector, right? Where you basically just negate the spatial side, okay? And then Dr. Miller is here, is like, I have to do all this conversion in her head, because in a lot of theoretical textbook, is actually we flip the time component instead of the spatial component, because why would you do three things instead of one? But the result is actually the same. So the main idea is that basically the signs between the spatial and the time components are opposite each other whenever you go from a contravariant to a covariant. And this allows you to do a dot product where you have x mu on with the index on the upstairs, and then x mu with the index on the downstairs. That tells you which one is which, right? So you have a contravariant dot product with a covariant. And when you do this, what happens is then you come up with t squared minus x minus y minus z squared. And that's actually a Lorentz invariant that we just saw in the beginning of last lecture, right? Okay, I'm going to apply this. So this is the coordinates, how you translate from one coordinate to another. Okay, in a lot of particle physics, what we're going to deal with is actually the form momentum instead. Okay, the form momentum, in a similar way, we're going to combine, instead of combining time, we're going to put energy as the first component of that form momentum. Okay. And then the other three momentum is just the, XYZ momentum of your particular particle, okay? And we form a form momentum just like we did with the spatial version of it, okay? Where energy, right, in order for you to get this correct, right, it's not E equals MC squared, it's E equals gamma MC squared, but we set C equals to 1, so we don't have the C's around, okay? So the energy of your particular particle is this gamma factor, the Lorentz factor, times the mass of your whatever particle we're talking about, electrons, protons. There is an interesting case when you have massless particles where basically the energy and the momentum are actually the same, but we'll get into that in a little bit, okay? Okay, and then momentum, of course, is the mass times velocity, right, in classical mechanics, but in relativistic mechanics, you have to put a gamma in front also, okay? Right, that allows you to correct for the relativistic effects, okay? So when we form this form momentum, so this is a which variant? Anyone on Zoom or on contravariant, right? Because someone on Zoom tells me why is it a contravariant? Okay, we got pretty quiet on Zoom. Okay, so the reason it's contravariant is because, right, you have the index on top, just like you do with the spatial four vectors, right? You have if your index is on top, it's a contravariant. If your index is on the bottom, you have a covariant, and you just have to make sure that the spatial part of the last three of those of components of those indices are actually negative of each other, okay? So if we were to write this covariant vector instead, right, I will still have the same sign for E, but then it'll be negative px, negative py, and then negative PZ. Is that, who is that? I think Cliff, you might have left your mic unmuted, so so we can hear some of your cough, but that's okay. You know, it's not too bad. But just in case you want to know that. Okay. Okay. So now, right, we have these definition just like we had before, right? When we do the dot product, remember when do the dot product, you do the Einstein summation rule, right? I'm going to do it on the right side here. I mean, like, you know, the answer is over here, but okay. So you have your momentum with the index upstairs, and then you have the momentum with the index downstairs, right? And the idea is that you're going to take the first component, you know, multiply them together, right? Okay, that'll give you E squared. The second component, multiply them together, right? The idea is that when you have the same letters, Greek letter index, right, you multiply the two numbers together, component by component by component. It's just like really taking a dot product, okay? So in this case, the second component will be px squared. The third component is, of course, negative py squared, and then negative pz squared, right? What you can do is combine all these three things together, right? Because, right, this, if you factor out, oops, the negative sign out of all of them, right? This is px squared plus py squared plus pz squared, right? And that's the magnitude of the momentum vector square, right? Right. So in a textbook where they just, instead of typing the vector arrow out, they just put a bold print to indicate something is a vector, right? So therefore, you have just the P mu is equal to just the energy square minus the momentum square. Okay. So does anyone recognize what this is going to be equal to? No, it's a little bit wonky. Have to remember all your special relativity relations. Okay, this may not look familiar, but what if I write this? Okay, so what is P mu, what is the, basically the for momentum dot product to itself equal to now? Can you guys see that? Yeah, it's just the mass square, right? Okay, this is actually the invariant mass square. So, okay, and hopefully it makes sense, right? So it's invariant because mass, right? No matter which frame of reference you are going to, right, you should have the same mass, right? It's just the amount of stuff you have inside you, right? How many protons, how many neutrons, mostly, right? You have inside you, okay? And typically what we do is then, right, if you have to deal with multiple particles, right, it's just like regular momentum, hopefully, right? You know, if you have, you know, let's go back to classical mechanics, right? So you have a car going, you know, in some direction with some momentum, P1, right? And then you have a truck. This is harkens me back to general physics, momentum P2, right? If you want to add those two momentums, the total momentum of the system, right, it's just the sum of those momentum added up together, right? So I equals to 1 to 2 in this case, okay? Just like that, right? For momentum, it's the same thing, okay? When you have multiple particles, you know, maybe two, three, as many as you want, or n number of particles, okay? What you do is you just add up their momentums, okay? So, I mean, let's just do a quick example here, right? Let's say I have a 4 momentum, maybe let's do the contravariant, let's say 10, comma, 0, 0, 10, right? You know, and this is all momentum, so this will have units of, remember what the units of momentums are? Oh, I think I gave it away. Oops. Well, you have to figure out what the power is. What's the power of this? It has to have the same unit as mass and energy in natural units. So what's the power up here? It's just what? Just 1. Oh, someone's probably said on, oh, right, okay. Anyway, okay, so let's say we call that momentum of, you know, particle number 1, but then we have a momentum of particle number 2, right? Let's say is, you know, 20, let's just make the math easy. So let's just make the X and Y component both 0 and then 20. It just has twice the magnitude. Okay. Oops, that's not a square, right? Okay. So the dot product between P1 and P2 will be what? Usually, I think you put the particle identification first, and then mu. Okay. So, 20 times 10 is 200, right? 0 times 0 is 0. And the last component is 200, right? Is that right? I see people nodding their head. Anyone on Zoom disagrees with me? This way? Right. Oops, let me just do it up here, right? So I define both contravariant for vectors, right? But when we do a dot product, we have to dot product the contravariant with the covariant, right? Either or. So the contravariant, right? If you move this index downstairs, this will make this a negative, right? So actually the Z component, the third component here should be negative 200. Okay. Oops. And I made another mistake, right? Remember when you do a dot product, this is kind of like think about it as a scalar product. You add them together, right? Look up my index notation, and this actually comes out to be 0. Okay, this is most likely probably like a gluon or a photon, right? It has no mass, right? Because this is basically the mass square of your thing, okay? I didn't pick that example specifically for that. Well, I guess I should have known because the energy and the momentum is the same between these two particles. So they're both massless particles somehow, okay? Okay. But I think I intended the example also to, right? We can also add these for momentum, just like you would add regular momentum, okay? Where P mu plus P mu 2, right? If you add them together, you just get, 30, 0, 0, right? And then this will be 30, right? You just add them 10 plus 20, just like before, okay? Okay, so that's the total momentum of like maybe two particles colliding together or something like that, okay? Let's call that P mu. Usually when you have the total, they don't put an index down here, right? Okay. All right. Some useful properties for momentum, just like 3 momentums, right? Momentum is conserved, hopefully, okay? Just like when you run, what was it, like usually I have a car run into a truck, right, together, and then you conserve the momentum so you can actually predict, one of the direction of the resultant vehicles. Same thing here, right, where let's say I have, particle 1 coming in, and this P stands for momentum, not particle, right? And it's scattering off another particle, right? Coming out. So this particle appear, even though it's the same particle, this will have some new momentum, right? That's going to be because it's scattered, so it changes its direction slightly, and maybe its energy also, right? And then you have momentum P4 here. So let's say we have a Feynman diagram going this way, okay? Right? So what I can say is that, well, P1 plus P2, right? And these are 4 vectors. I'm not writing the index, okay? Okay, it's going to add up to what? Plus P4. Yeah, right? All of this harkens back to all of your general physics, introductory physics stuff, right? And where right now it's just a little bit more complicated because the 0 component is actually energy, right? Okay. Okay. All right. And I think I kind of already mentioned this, but for a massless particle, right, up here, the one I defined up there, I can just write it again, right? The P1 that I wrote, right? What was it, like 10, 0, 0, 10 or something like that, right? Right. This is a massless particle because remember, this is the energy component, right? And these three is the momentum component. So the magnitude of the momentum here is also 10, right? So therefore, for a massless particle, the energy is equal to its momentum. Okay. So for example, a photon, right? The energy of a photon is the momentum times the speed of light. But in our case, right, since we're using natural units, we get rid of the C. So just E is equal to P without having to do any conversion factors, right? Which is nice. Just to show you guys one more thing, right? In general physics or your E&M class or something like that, if you had that, the more advanced version of that, right? We typically, if we have a plane wave going from left to right, like in this case, this little drawing here, right? The electric field is oscillating up and down. The magnetic field is oscillating in and out of the board. Let's see, minus 200. Yeah, so Brandon, you're right. Right, the way we describe this electromagnetic wave is that, you know, there's maybe some amplitude of this electric field, right, times some cosine function, right? And this cosine function is described by this kx minus omega t. Does anyone remember what k stands for? The what? The wave number. Yeah, the wave number. This is a wave number, right? And it's very unintuitive what a wave number means, but in natural units, it's actually pretty intuitive, because if we go back to here, right? So the energy of a photon, right, is hf, Planck's constants, times the frequency of that particular photon. Well, if you're interested more of a wavelength, right, it's just h over lambda c, right, where I'm just using the fact that the speed of light is going to be lambda times f, and then you solve for f, and then you put that in there, right? Okay. So what you can do is then, well, of course, h bar is related to h by just over 2 pi, right? Okay. So what I can do is get rid of this h and put an h bar with a 2 pi in front. That's the same value, right? Whatever that is. Okay. So it looks like E, right, is going to be equal to some constant h bar over c. But since in natural unit, we're going to set both of those to equal to 1, the energy is going to be equal to 2 pi over lambda. Okay. And what's 2 pi over lambda for electromagnetic waves? Okay, I think I'm trying to get you guys to remember a lot of stuff. That's just K. Okay, which is also the momentum of that photon, right? So the wave number is literally just either the energy or the momentum of that particular photon, right? It's kind of neat. It makes without having to deal with like SI units, it just makes things a lot easier to understand conceptually, actually, right? Okay, because if you're multiplying that number by h bar over c, is that really the same thing, right? Okay. Main thing is that, right, the higher the energy of the photon, right, the shorter the wavelength, and since the wave number is inversely proportional to the wavelength, basically energy and wave numbers are proportional to each other, and that constant of proportionality happens to be h bar over c, right? And then if you set those to 1, you don't have to deal with them at all. Okay, more on chat. Yes, exactly. Sorry, I should actually just ask people on Zoom first, and that way it takes a little bit longer to type your answers, right? Nice background, Baccarin. All right. Okay. So there's a little situation with notation now that we have like regular vectors and 4 vectors, right? So there's a little notation situation here where, you know, I think this book calls it the dot product. Some people call it the invariant products because it is a Lorentz invariant. Some places will see it as a scalar product, just like in the old days when you have dot products between 2 regular vectors, right? And you would just call it dot vectors, right? So all these different products, right, they're all similar, but not quite the same, right? Because what happened is that if we're asking for the product, whatever you want to call it, of a 4-vector, right? You always are calculating the contravariant multiply dot product it with the covariant, right? Okay. No matter which, I'm not sure that this little bar is necessary, but okay. Okay. Where in normal sense, right? So whenever someone say p square, right, in this book, they really mean p mu, p mu. Okay. Okay. When they write p, when I write p dot, they mean the 3 vectors version of it, right? Oops, go ahead. Oops, where'd it go? So 3 vector, when they say p square, they mean the 4 vector version of it. Okay, and this is especially like annoying in the textbook, right? Because in textbook, what they do is they just do p bold p, right? And if they do a square here, right, this means p dot p, right? Where they have a lighter p, I'm trying to write a lighter p, right? They actually means p mu, okay? Isn't that fun? Okay, all right. One more little notation thing, okay? Okay, so we know that p square, right, is actually equal to, without the bold, right, it's actually the mass of your particle square, okay? Right, so p is actually equal to the magnitude of p, right? In the textbook, what they do is they just write the magnitude of p is always m, right? Okay, for a massive particle. For massive things, you have to take into account that, well, this is going to be equal to 0. But so in order to write in this textbook the magnitude of a 3 vector, what they do is they put p star. Okay, that's the magnitude of a 3 vector instead. Okay, yeah. It's just a little bit of just make sure that all the notations are slightly different. Okay, so just, I mean, in the beginning, just have it on like a little sheet of paper on the side here, right? Just a little note. Okay.
I have a question,
Yes.
Dr. So if
Yeah,
they
go
use
ahead.
a star, so how the textbook shows conjugate then if they are using a star?
The
Something
same,
else.
the complex conjugate would be the same symbology.
Okay.
Um,
Yeah, it's
and
complicated.
from which context you have to know which one it is. So if it's a matrix, it wouldn't be that, right? So that's the complex conjugate of a matrix. And what's going to happen is that we're actually going to not use complex conjugate by itself anymore. We're going to start using what's called the dagger, which is a transpose plus the complex conjugate. Because what's happening is that when you move things from upstairs and downstairs, you're technically doing a transpose of that particular vector or matrix or whatever object you're talking about. So whenever you're having a product, whenever you have to product 2 things together, you always have to do a transpose anyway. So, and that symbology is like some matrix dagger. So that's the same thing as doing a transpose and a complex conjugate on that particular tensor, matrix, vector, whatever you want to call it. Okay. Yeah.
Thank you.
The invariant product and what is the same? The 4 vector, but yeah, they are the same thing. They just, different people will say different things, and even in this textbook, they will say different things at different times. So there, for each type of things, there's only one scalar product type of thing you can make, right? That makes sense, at least, right? So for 4 vector, it's always going to be this Lorentz invariant or the 4 vector dot product. For 3 vectors or the normal vectors, then you just do your regular dot products. Okay. Okay. You just have to be careful with 4 vectors that, okay, if you're dotting it to itself, you're going to have the negative of the spatial component all the time instead. Okay. Because otherwise you don't get a Lorentz invariant. Okay, so let's finish up this just to show you guys a little bit more mathematics that you can do, and we're going to see how this will become very useful when we get into the next chapter. So there's also 4 derivatives, meaning you can take derivatives of things and have it also be contravariant and covariant. And then if you take 2 derivatives, then the 2 derivatives will actually be a Lorentz invariant also. Okay, so to show you how these derivatives actually changes, I don't think we need to go through a lot of these mathematics, but I think it's good to kind of review your maybe this is like calculus 1 when you have a chain rule thing, right? So if I want to figure out how does the derivative with respect to a coordinate in the prime coordinate system, let's say along the direction of z changes, okay? In order to figure that out, right, I need to know how does the coordinate itself changes in the unprimed, the original, let's call it the non-moving frame of reference, right? And then how does the 2 frame of reference actually changes with each other? Okay, that's sort of like a little bit of a chain rule. Okay, this may be a lot clearer if I just wrote this. If I want to take the partial z by partial z prime of this z function here, right? This is the z function, right? Gamma z prime plus, wait, do that right? Yeah. Oops, don't jump to a different window. Okay, maximize this. Okay, beta times t prime. Okay, right, what I need to do, so this function depends on z prime. I copy the wrong equations over. Yeah, okay, sorry. I want the other one. I want the prime version of it, sorry. Okay, and that switches the sign. Okay, so yeah, so sorry for that. I actually want to take a derivative of this z prime function. I just copy and pasted the wrong one, right? Remember when we go from the prime to unprime, Lorentz transformation, the only thing you're changing is the sign of the velocity. Okay, so it's pretty easy to switch between the two. Okay, if I want to figure this out, I need to know how does this depend on z prime, and how does time also depend on z prime, right? That's the funky thing, right? Because it depends on not just z, but also time, okay? So this breaks up into this little chain rule where, oh, you have to figure out how does it change with z itself, and how does it also change with time itself in the non-moving coordinate system, okay? All right, let's not deal with the time part first. Let's just look at this for now. So in order to figure this out, right, I need to figure out, well, what is the partial derivative of z with respect to z prime, okay? If I just take this partial derivatives here, the partial derivative of z with z prime is just gamma, right? Because if I did the partial derivatives here, the t is constant, right? You just ignore that. And then you have, the derivative with respect to z, which is just going to be gamma times z, which is just actually gamma. Okay, this little piece here, right? Once again, we're going to go back to over here, do a little erasure, right? If you take the partial derivative of the t function, which is over here, I need to actually write that one, right? T equals to gamma times t prime plus beta times z prime, okay? If I take a partial derivative of that with z prime, right, you end up with gamma times beta, right, as the factor in front of z prime. Okay. Once you have that, right, you can plug both of those in there to figure out what the derivative with respect to the moving coordinate system, okay, as a function of derivatives of the non-moving coordinate system. Okay, I know this may not, like, why are we doing this, right? I know we're just setting up a lot of math, okay, so that we can actually do a Lorentz invariance of derivatives also, okay? And of course, to these factors in front, right? This is gamma, and this is the gamma times beta, right? That's from us taking the derivatives with respect to each of the variables individually. Okay. If you do a similar exercise, especially since I'm a little bit low on time, right? If you do a similar exercise, you're going to see that the partial derivative of with respect to the moving time coordinate to figure out how to calculate that with the function that's in the non-moving coordinate, which is meaning you're doing derivatives with respect inside the non-moving coordinates. You also have these gamma, beta, and gamma factors in front of it. Okay, so that's the only difference. Okay, right. And if we put all these derivatives, right, put the time component as the zeroth component, and then the spatial component as 1, 2, 3. Okay, you're gonna see that this is gonna look a little bit familiar, right? Where you can do a little matrix multiplication of them instead, right? Transform this sets of 4 equations, right? Because you have a partial by partial x prime version of it, which is just partial by partial x because it's not moving. Partial by partial y prime, which is equal to partial by partial y because the frame is not moving in the x and y direction relative to each other yet. Okay. And then if you put all these 4 equations, just like what we did with the spatial coordinates, okay, you can put this in a vector like this going downward, a column vector, multiply it by a matrix and get the result that you expect to happen, right? So this is the Lorentz transformation, well, the inverse Lorentz transformation matrix just as before, okay? So that's pretty nice because, right, then we can do a very similar thing as what we did with the spatial coordinates, okay? So what we can do we can define what's known as a covariant derivative, right? Where the covariant derivative is the same thing as partial by partial mu x with the index mu, and we're just gonna call that equal to the partial mu, okay? Just to shorthand things, okay? Okay, because basically what you're doing is that this mu indicates whether you're taking derivative with respect to the time component, the x component, the y component, the z component, right? You don't need this x mu down here. Okay. Okay. All right. So for the derivative case, okay, the covariants, okay, are going to be the positive part. So this is another thing to unfortunately have to remember, just because the way that the Lorentz invariant changes from one frame to another, you have to kind of keep track that, okay, well, if you're taking derivatives, okay, the covariants are the one without the negation, okay? Where the contravariant is the one you do negate, okay, the spatial part, okay? But don't worry, most of the time, since we're going to be dealing with Lorentz invariants anyway, what you want to do is actually do partial mu, partial downstairs mu all the time anyway, right? Because this is actually a Lorentz invariant derivative. It has to be a second derivative because you need 2 of them, okay? Right? And when you do that, what you end up with is basically the second derivative with respect to z, the second derivative with respect to y, the second derivative with respect to x, all with negative signs in front of it because of these negative signs in the contravariant, okay? The time component is the one without the negative sign, okay? And this is used so much, instead of, you know, writing partial mu all the time, people just draw a box, okay? It's actually called the Bramsian, Bernsian. Yeah, maybe someone who say that more often will know how to actually pronounce it.
I always say D'Alembert. I don't know
Yeah.
if that's right though, but
or ancient.
D'Alembert.
Yeah, I just call it box.
Yeah,
Okay,
that's what I say most of the time too.
we just call it box. Okay, when you box a function. Okay. All right. Okay. Just to reiterate and be a little bit clear, I think we already kind of went through this notation stuff. Just to make sure you're clear on the notation, right? 4 vectors are letters with Greek letters or sometimes without it. Okay, three vectors in the textbook should always be bolded, right? When you're writing it on paper, I think the arrow actually makes a lot more sense. Okay, And then when you do p square is actually the, you know, the 4 vector dot product. But then when you have bold, the book does the bold p square, that means it's actually the 3 vector dot product, right? It's like slightly different. Okay, because you don't negate the spatial part. Okay, it doesn't make, actually, if you just always negate the spatial part, it doesn't make a difference, right? No, it does. It actually gives you the negative of the number. Never mind. Yeah, don't do that. Okay. And p by itself is the magnitude of a 4 vector, where p star, right, is the magnitude of a 3 vectors. Okay, and just to confuse it with complex conjugates also. Okay. Just to wrap up here, right? And then let's start with the Mandelstam variables on Friday, and that way give you guys more time to start, you know, looking at the homework and how to grade it, so I can answer questions live here. Okay, so I'm going to stop sharing and stop recording.